Okay, welcome everybody. It's the top of the hour, so we're going to go ahead and get started. I'm Mahida Awad, I'm a past president of the National Association of Geoscience Teachers and one of the three representatives sponsoring this webinar series, which is the NGSS ESS webinar series. In the middle of the screen that you see in front of you there, you see some guidelines for using Zoom. So down at the bottom of your screen, if you hover over, you should see this toolbar. And this is how you will get to the all-important chat box right here. And chat box is really important because we always encourage webinar participants to enter thoughts, ideas, questions, comments into the chat box during the course of the webinar. So Michael has said that he will stop periodically to check on those questions and to field some of them. But please keep them there and we'll keep track of them for you. So and enter chat questions into the chat box as we go through. Nicole, do you want to go ahead and forward the slide one? Thank you. All right, so here on this slide, you can see the title of today's webinar, Beyond Earthquake Locations, Modern Seismology in the NGSS Classroom. And as always, the organizer of this webinar, myself, Aida Awad, also with us, Ed Roback from the American Geosciences Institute and Carla McAuliffe from the National Earth Science Teachers Association. And behind the scenes doing all the great work for us is Andrew from CERC. Can you forward the slide one, please? Also, the webinar is being recorded and I can see that it is currently being recorded. So excellent, thanks Andrew. Our upcoming webinars, we're very excited to announce a webinar mini-series. No, this isn't Netflix, no it isn't Hulu, but we've got a mini-series too. In March, we'll have two webinars back-to-back, 2 weeks apart. March 5th webinar, which will be entitled Teach Students How to Ask Their Own Questions to Explore Phenomena in an NGSS Classroom. This webinar will be presented by Sarah Westbrook, who is from the Right Question Institute, and Nicole Bolduc, who is a middle school teacher in Ellington Public Schools and becoming quickly well-known on the workshop circuit, talking about QFT, question formulation technique, and asking questions. That webinar will be followed closely by the March 26th webinar, which is entitled How to NGSSify the Question Formulation Technique. And so we hope that you'll join us for those two. Registration is always already open. I sent out an email, you should have seen that about the middle of last week. And then in April, we'll have an exciting webinar, which will give you some insights into a wonderful new series of activities and modules that comes from the Lyda Hill Foundation's If Then Ambassadors. And these will be curriculum connections coming through Lyda Hill Foundation and the American Geosciences Institute. All right, so today's webinar will be presented by Michael Hubenthal from IRIS, and post-webinar we'll have time for Q&A discussion, and then we'll have the survey at the end of the webinar. Go ahead and advance it. I think, yep, just a reminder here to please type your questions into the chat box during the course of the webinar. All right, I think we're ready to go, Michael. Floor is yours.
All right, well, great. Thanks very much. I'm grateful for the opportunity to be able to share some ideas about seismology education and what that might look like as we move forward into increasing the number of NGSS-aligned classrooms that are out there. So that'll be the main focus for today. So one caveat that I like to give when I start off these sorts of sessions is to say, first, that I'm not a seismologist myself, so there may be questions that come up at the end that I need to take a few notes on to help connect with the right people to kind of get answers to those questions. But on the other hand, I've been working on seismology education issues. My background's in science education, and I've been doing this since 2003 for the IRIS Consortium. So I can field probably most of the questions, but we may reach those limits. And if we do, we can get answers to those questions. So let's go ahead and talk a little bit about what we mean by seismology. So seismology is the study of elastic waves and their sources. And there are two types of data that we usually collect for this. The first is going to be in the top right-hand corner. We have time series data, which is going to be showing us seismograms, recordings of ground motion at various locations around the world. And this can be sort of, continuous time series data, hours and hours to months of data. or we might be looking at just little snippets of data that happen around particular earthquakes or things of interest that we want to examine. The other type of data that we might want to, the other thing that we might want to pay attention to is that down here in the bottom, we have event data, and these are going to be details of an actual earthquake that takes place somewhere, like the date, the time, the latitude, and the longitude of that event, its depth, its magnitude, and that sort of thing. And so these are all put together in catalogs that are then used for things like studying and forecasting earthquake hazards. We're also going to be using some of these time series data for things like deep earth structure studies. We might use them to study, fault rupture mechanisms, and we might use these things to study things like explosions or monitoring for the Nuclear Test Ban Treaty. These are sort of the common traditional uses of seismology. However, what's really exciting right now is that we're applying many of the techniques for studying seismology, some of these more traditional topics. We're applying these now to new areas of science. So one that's currently being studied is storms, for example. There's active research going on right now where we're using seismographs around the world to begin to measure and better understand hurricanes and tornadoes. We're using seismometers to be deployed around karst systems to understand groundwater flow through karst systems. We're using them similarly to measure bed load in fluvial systems, especially during flood stage, when other systems that are more traditional are unable to keep up and actively monitor the bed load just because of the sheer volume of water that's moving. We're also studying glaciers with seismological techniques, and even using seismometers to make estimates of sea ice coverage in certain areas where we might not be able to actively see them by studying the microseisms or the waves that are crashing against the coastline or the continental shelf, and we're able to see that on seismographs. All right, so I did want to do a quick poll. Now that we've got a little bit of background on the types of data that we might use, I'd like to do a quick poll on how people might use this data in the classroom. So the first poll question that we're going to be asking about, and you should get a poll that pops up for you. The first poll question is going to be, what grade level were you primarily teaching at? The second question that I'd like to know about is ways in which you currently use seismograms as part of your instruction. And then number three, ways that you currently use that seismic event data as part of your instruction. So we'll give people a few minutes to answer those. Okay, great. This is really helpful for me to kind of see the way in which people are using seismic data. And I think it would be really interesting for you to take a look at as well. There's some common themes there that we might want to pay attention to. In fact, I'll touch on these as we continue on. So thank you all for answering that question. All right, so what we'd like to accomplish by the end of the session today is, number one, I'd like you to be able to describe just a little bit about the SAGE facility. This is the facility that's operated by the IRIS Consortium and that I work for. We also want you to be able to find educational resources and data sources on the IRIS website. And finally, we'd like you to be able to describe at least one way that you might go forward and modernize the seismology instruction that you deliver in your own classroom. So I think the place to start is by just a little bit about the SAGE facility. So SAGE stands for the Seismological Facility for the Advancement of Geoscience. It's funded by the National Science Foundation as a research facility, and we have three main programs that we operate at the SAGE facility. The first are instrumentation services, and this group is responsible for the deployment and maintenance of seismic instrumentation around the world. This includes both permanently installed stations that are monitoring for deep earth structure studies, nuclear test ban treaty monitoring, as well as pools of temporary deployment instruments that might be, for example, ocean bottom seismographs that are going to be deployed for short time periods and then recovered, or terrestrial-based systems where we might deploy high precision or high frequency sensors over locations for anywhere from a period of a few days out to a couple of years, and then those instruments are all picked back up. We have staff to go out, service these equipment, help deploy them, and help make sure the experiments go smoothly. The second program that we have is the Data Services Program. This is the world's largest repository of seismic data. We have data being streamed in from geologic surveys all around the world. This data is curated by our staff and prepared to be served back out to the community who want to use it for research purposes, as well as those who want to use it for education purposes as well. So all of the data that we hold is freely available for anybody who'd like to access it. And one of the things that we work on is providing a variety of ways to get at that data that would be most appropriate for the audiences that want to reach it. And finally, the third program that I work for is the Education and Outreach Program. And here I put a variety of the staff who work for the Education Outreach Program, because many of the products that I'm going to be showing in this talk are produced by them, and so I want to make sure they get credit for their work. I get to show it, but they have invested a lot of time and hours and thought and energy into creating these excellent products. So if we're going to talk about modernizing our seismology instruction, I think it's worth talking a little bit about what traditional seismology instruction would look like. So I think what you're seeing up here on the screen kind of matches what I expected from the poll. A common way to use event data is by an epicenter plotting activity, where you get a list of earthquakes and you have students plot those around the world and begin to look for patterns in that data. The second activity, often done in combination with the third one, is taking a look at some seismograms and doing a few things with those seismograms. We might locate an earthquake using the S-P location exercise, where students pick a P arrival and an S arrival. They subtract the arrival times of those to then use a travel time curve to look at how far away that event actually is from the epicenter. And then the final thing is calculating a Richter magnitude. And so we use nomograms. There's an activity online on the Virtual Seismologist website that's quite popular, where people go in and you can then measure the amplitude of the waves and then use the nomogram to look up what that magnitude would be based off of how far away that event actually is. So what I'd like you to do right now, everyone just take a minute or so. I'll give you at least 60 seconds to do this, maybe even a little bit longer. I'd like you to jot down a few ideas on scrap paper that you have sitting there. You could even type them in the chat window if you wanted. But think about what you're trying to accomplish with these activities that you're using. And I'd like you to think a little bit about how they fit into the current NGSS standards. So it's a broad question, and we only have a little bit of time, but put down a few ideas about one of those aspects, either how or why you use them, what you're trying to accomplish, and then and or how they fit into NGSS. Okay, I've been monitoring the chat window, and hopefully those of you, others of you have been jotting down some ideas yourself, just on some paper. But there's some really interesting themes that are coming out in the chat window, and they're common across a lot of the responses. And I think they're important. They're dealing with the idea of using scientific data with students and helping them to engage in the scientific process, and also the use of real-world events. You know, earthquakes are inherently exciting things to students. They're sudden, they're unexpected, sometimes they're catastrophic, and so they're really attention-grabbing. And so that's a common theme across ideas about why people might be using those. So when I did a little reflection on where these fit within the NGSS, I started by looking at the use of event data, right? This idea of epicenter plotting, for example, might be one activity that we would do. And one of the things that I quickly noticed was that the role of event data is kind of shifted downward in the NGSS. You know, we see as early as in 4th grade where we're asking students to analyze and interpret data on maps to describe patterns or features on the Earth's surface. And this specifically includes earthquake data. So here we might be asking students not so much to identify plate boundaries, but we may be asking them to look at the relationship between where earthquakes take place and, say, the location of mountain ranges, or the depth of earthquakes and the depth pattern of earthquakes, similar to what I show here in the IRIS earthquake browser, and then the onshore mountain ranges down along the coast of South America. And from there, we can then get into, in middle school, the idea of using this event data to better define the idea of plate tectonics, looking at plate motion and plate boundaries and that sort of thing. And so they are it's well fit into the NGSS, although at a slightly earlier age than maybe we have traditionally been teaching some of these concepts. It would not be uncommon for a middle school classroom or even a high school classroom to do some of these activities that we might be asking students to do now at an earlier age. We're not going to spend a lot of time taking a look at this tool, but I would encourage you to take a look at the IRIS earthquake browser as a source for getting access to event data. You'll notice on the right-hand side of this tool, if I can mark it up, on the right-hand side of this tool, here you have the ability to filter the data, going back to the 1960s to choose the number of events that you want to display, the region of the world you want to look at, time ranges that you want to look at. And then what's nice is you can export that data into various formats, whether Excel or a table format, so that you can then have your students actually work with that data and do things. So it's a useful tool. The URL is here on the screen, but it will also be in the slide deck at the end if people want it. So the next place that I wanted to look at is, all right, there we go. Sorry about that. I had to clear my annotations, and that was proving difficulty with advancing my slides. So the next thing I wanted to look at is how do seismogram activities fit into, the traditional seismogram activities fit into the NGSS. And it turns out that when you read through all of the standards, things like earthquake location really aren't explicitly part of the new standards. We use earthquake locations, we use seismic waves, there's explicit mention of those sorts of things, but they don't really come up that explicitly within the standards. The other thing that I would note here too, in terms of a discussion of modernizing your seismology instruction, is that the act of using S-P locations is a little bit dated. You know, earthquakes haven't really been located in this way since before the 1960s. And from an instructional point of view, a concern that I have is the overemphasis on the sort of crossing of the circles, right? The idea of a right answer being what you're after here, the point where they touch. And this becomes problematic for students because, number one, they're commonly using compasses on flat maps. So they're trying to solve a three-dimensional problem on a two-dimensional map. They don't have a ton of practice with compasses in general. And the other thing too is that in order to really be able to identify both P and S waves, they're tough to identify in actual seismic data. So what ends up happening is many students are using synthetic seismic data, or even then, sometimes they're hand-drawn wiggles on a page, simply to show that bump 1 is P and bump 2 is S, even though that's highly simplified when we start looking at seismic data. In fact, if we were going to do this activity, we would actually want to use 3-component seismic data that would include, both directions of horizontal motion as well as vertical motion, because P is strongest generally on the vertical component, and S shows up most strongly on the horizontal components. And the other concern that we have, of course, too, is with Richter magnitude calculations. Again, another dated technique. Richter magnitudes are no longer used. They're really only applicable to California or the greater California region when they were first created. And they're dependent on the use of a Woods-Anderson seismograph, which is no longer produced and really only maintained in places like the Weston Observatory at Boston College, where they're maintaining historical equipment in order for the purposes of comparing data over many different years and many different instrumentation types. So there's a few concerns that we have with some of our more traditional seismogram activities that we use in the classroom, which makes these ripe targets for doing some updating. So I'd like you to, take a quick pause. I'll open the chat window that I've closed because it's a little distracting for me, and see if there's some questions in there that maybe we want to field. And you might want to take a minute or two and jot down some ideas about some of the things that we've been talking about.
Hey, Michael, this is Ada. I've been having some conversations with a couple people here about Richter magnitude versus moment magnitude, and you were talking about modernizing instruction. I'm wondering how you recommend we think about those.
That's a great question. What we encourage people to do when talking about magnitudes, because there's many different ways to calculate magnitude, even besides moment magnitude and Richter magnitude. So the answer that we usually give is, if you say magnitude, you will always be correct. If you say Richter magnitude, you will almost always be incorrect, because the Richter magnitude calculation isn't used anymore for the most part. And the key for seismic moment is, for moment magnitude, is that we're calculating some of the more physical parameters of the fault rupture. So the seismic moment is, if you think about physical science properties, it's the length and the width and the displacement of the fault, how far it actually ruptured. And so that gives us what we call the seismic moment, or the energy released by that, which we then scale up to the moment magnitude scale to get onto that traditional one to sort of, well, technically it's infinite in either direction, but we can tend to think of earthquakes as being, sort of 0 to 10 ballpark range. And that's how we get there, is by scaling up this seismic moment calculation.
So when our students hear a news report that says the magnitude was 6.3, what are they reporting?
Yeah, they're almost always reporting moment magnitude now. There's a few cases where they might be using a slightly different type. But I think the key here is, for most people, it really doesn't matter what type of magnitude, because they're all made to scale to one another. And so it's best if we just say magnitude. And if the students want to learn a little bit more, for example, they might use the earthquake machine activities that we have, where we have an actual fault block that slides around. And you can begin to think about the amount of energy that that block would have when it's moving, as if the block were twice as big or 3 times as big, for example. Would be a larger energy release, which would then be scale up to a larger magnitude event. Okay.
Michael?
Yes.
This is Rebecca Dodge. I attended a week-long IRIS training in Austin several years ago that was provided for the teachers who work with educational resource centers in Texas. And we built the earthquake machines, and I got back to my university and I built earthquake machines and did teacher training with those. And if anybody on this call has never actually put one of those together, you have to do it. I just can tell you, it's a wonderful experience for your students.
Thanks for that. It was a fun workshop. I do remember presenting there quite vividly. It was a great group of folks, and it is a great activity. It's a really engaging activity. Gives students a chance to collect data in the classroom. as part of in a section of the geoscience unit where they traditionally might not have a chance to collect empirical data on their own. So if I get a second at one of the breaks, I'll try to put in a URL here to see if I can share that in the chat so people can get access to it.
It's very effective in the classroom.
Okay, so let's kind of move on here. So what could we do? Whoops, I'm going to get back one. So what could we actually do if we wanted to try to modernize the seismology in your NGSS classroom? Well, this might be shocking to some, but one thing we could do is drop earthquake locations. And we could replace that with a more aligned activity using seismograms. There's other things that you can actually do with students in your classroom using seismic data that is better aligned with the standards and actually might help them learn more important topics than the process of triangulation, for example. So one example of what that might look like would be exploring the interiors of terrestrial planets. So there's a high school standard that specifically calls out looking at seismic evidence to develop a model for Earth's interior. And this is one of the activities that we can do very easily with seismic data with our students. And so I'm going to walk through this activity a little bit with you here in this webinar. It would be a great activity to get your feet wet in the webinar and then download the materials and take a look at yourself because there are a number of steps in it, but the end product is really quite surprising for most students. And I think most people have quite a lot of success with it. So let's start off by asking the question, how do you personally know what's inside of the Earth? And I'll tell you, when you ask this question, to your students, you'll get things like just showed up in the chat, like, well, I know there's dirt down there, I dug a hole. Or you might have had a student that's walked past a large construction site in an urban setting and they say, well, down there, you get down to there's rock down there, there's concrete down there. Some may have been to a cave and they may, say, well, it's definitely rocks. I've been to a cave, it's really deep and I've seen rocks all around me, or a quarry. So we can get to this idea with students that they do have some direct experience with what's below the surface of the Earth, although it will vary highly across the students that you might have in your classrooms. A number of them will try to answer this question by saying, well, the Earth has a layered interior. And then when you press them and you say, well, how do you know that? How do you really know that? And they all suddenly begin to realize that they don't really know that. They've seen it on the Discovery Channel. They've read it in a textbook somewhere. They maybe have had an instructor who's shown it to them in the past, but they really don't know how we know that. And so that's really what this activity is all about. It's about discovering and measuring Earth's layered interior. So this group is going to divide up, you're going to divide your class into two groups. There'll be seismologists in one group, and they're still going to use seismograms. They're going to use what we call a record section of seismograms. And the record section shown here on the left has time since the earthquake on the y-axis, and distance from the earthquake is plotted on the x-axis here. So the sort of brownish seismogram is the furthest away from the event at, in this case, it looks like maybe 160 degrees away from the earthquake, with blue being the dark blue on the far left being the closest, it may be a few degrees away from the earthquake. The other half of the class are going to be theoreticians. And this part of the activity is really going to emphasize the science and engineering practices aspects of the NGSS, because these theoreticians are going to actually develop a model that we can then compare with our observed data. And so how this works is seismologists are going to look at their record section, distance away again on the x-axis, time since the earthquake on the y-axis, and they're going to go in and we're going to mark on each seismogram when the seismic waves first arrive. And we could even say, when do the P waves arrive, if we've already covered different types of seismic waves with our students. And they can go through and relatively quickly discern what's background noise, and they can then discern when the first seismic waves arrive. And they're really going to just record the travel time. So what time did the energy actually arrive at each station around the globe? Meanwhile, the theoreticians are going to get a scale model of the Earth. So it's two pieces of 8.5 by 11 paper, printed at a ridiculous, or scaled down to a ridiculously small scale to fit. They're going to tape the paper together. In the center is marked a red dot with the center of the Earth, and the curve is the surface of the Earth on the outside. And so, like the students' direct experiences, which the deepest most students will have been will be a cave or a quarry where they've seen lots of rock. So we're going to assume in our model that the velocity of a P wave is going to be 11 kilometers per second, which is about the velocity of P waves in rock. So all the way through solid rock, right? The simplest solution to the problem is that it's all the same thing down there, which is what was actually thought before we had seismic studies of the Earth. So because it's a scale model, the theoreticians can use their model to predict with a velocity of 11 kilometers per second when the seismic waves should arrive at various degrees around the Earth's surface. So we have an earthquake that takes place in the lower right-hand corner of our scale model, and each triangle represents that we've drawn onto the surface represents a seismic station. And then I can just use a ruler, or in this case, for some of the distant ones, you need a meter stick, measure what that travel path is for that seismic energy. And then I can just simply do a series of conversions to get from the length of the travel path to a time by using velocity to predict when the seismic waves should arrive at various distances around the Earth. So now you have half the class with observed data, and half the class has now generated model data for when those should arrive with our assumptions of 11 kilometers per hour. If you wanted to be creative, you could allow a few groups to vary the velocities of their model. So maybe you want to have somebody assume the Earth is solid gold. If you get online, you can Google a P wave velocity in gold or other metals, other materials, just to add some interest to some of the groups, and you could make comparisons. So then at the end of the day, we want to have the two groups bring their data together, and they can plot those up on an Excel plot. They can graph them by hand, or if you're short on time, you can just simply create one plot for the entire class in the front of the room. But here on the screen, you'll see observed data plotted in blue, and model data will be plotted in red. So the question I always ask students is, how well does it fit? And not surprisingly, students who haven't looked at a lot of data frequently will start off by saying, well, it's great, it's pretty good. But then if you push them a little bit more, they'll say, well, I say, is it all good? And they say, well, not all good. There's some places where it doesn't fit real well. And I say, okay, great. So tell me a little bit about that. Why do you think that might be? What's going on there? And where does that take place? That's another important piece. And so most students can see pretty clearly that between that the last three bits of observed data don't line up very well with the model data, that we have some discrepancy happening beyond 100 degrees, but not to, maybe 115, 118 degrees. Somewhere in between there, something happens or goes wrong with the model and the observed data. And so we want to find out what that could be. So the next step of this activity, now that we've established that the homogeneous model doesn't match our data, is to say, well, what could be going on inside of there? And so we give them a second scale model and a protractor, and we have them say, all right, well, let's assume about 108 degrees away. Everything worked up to 108 degrees away. And so I'll try to mark this up again. That would be this section out here and this section down here. That all worked really well. However, out here, beyond 108 degrees away, we had problems where our data just didn't match up. So I asked them to cut away the part that worked, leaving only behind the part that that didn't work. And so they end up with a again the same. There we go. So then we end up with a shape that looks something like this. So they've cut out this sort of ice cream cone shape. And then I asked them, okay, lay that ice cream cone shape on top of another model. So the ice cream cone shape that you see here is actually sitting on top of another scale model, a circle. And I asked them to trace the edges of these lines. And so the earthquake happens at the red dot. everything, out to 108 degrees works, beyond 108 degrees doesn't work. And then I asked them, okay, now rotate it so you have had 2 earthquakes on opposite sides of the Earth, and then a 3rd earthquake and a 4th earthquake. And you keep just rotating this. And as you keep rotating this around on the paper and you keep tracing out that 108 degree set of lines, you begin to define some object that is in the way or causing a problem between our observed data and our model data. And it turns out that if you spend a little bit of time and you measure the dimensions of this object on your scale model, you can calculate the core of the Earth within a few degrees of error with your students. So they've used paper and pencil on a ridiculously small scale model, but they really get an accurate idea of the size of the core inside of the Earth. And they've discovered it with seismic data. So it's a pretty cool finding that they end up with. So where do you go from here? Well, now that you've established that we have to have a core in there, we could spend a little bit of time exploring some of those ideas about what's going on inside of the Earth. So I did want to take a moment and showcase an animation that we put together. We have a whole suite of about 130 different animations supporting seismological topics. This happens to be one about a brief history of how we found out what's inside the Earth. I'll show a minute or two of this just to give you a sense of what our animations are like, and also to give you a little bit of background about that activity that we just completed.
Much of our knowledge of Earth's insides comes from monitoring the thousands of earthquakes that occur every year. 5 centuries ago, the world had mostly accepted that the Earth was not only a sphere, but was thought to be of uniform rock throughout. 200 years later, Sir Isaac Newton, studying our planetary system, calculated that the interior of the Earth must be made of far denser material than the surface rock. Newton's estimate of the overall density of the Earth remains essentially unchanged today. In the early 1900s, scientists discovered they could use data from earthquakes as a method for looking deep beneath the surface. By understanding the travel times of different seismic waves to worldwide stations, scientists were able to calculate where boundaries occurred and what those boundaries represented. They thus determined that the Earth has 3 layers based on chemical composition: crust, mantle, and core. As an analogy for relative scale, these layers can be compared to an egg with.
So I'm going to stop the animation there, but as you can see, we basically performed what Richard Oldham had done in 1906, and we used data from a recent earthquake that we were able to pull down. In fact, you can pull from the most recent earthquake, so you could use the recent Caribbean earthquake. We also had a 7-point something that happened just off the northeast coast of Japan within the last 24 hours. You could use data from that earthquake to discover the core of the Earth. It's all available to you through the activity. You go into a special URL to get that data, and the data comes pre-formatted to be able to use in the activity as a record section. So it's really easy to use. The other tool that I would just quickly, I want to just quickly mention is this seismic waves tool. So it's in your web browser, and it allows you to investigate how waves propagate into the core in a variety of different levels of detail. So you can have the most detailed version where you look at phases like the PKIKP, where it's going into the core and coming back out of the core, where you can see reflections and refractions. Or if you choose to change the labels on it, you can simplify this way down to really just show the direct P and S arrivals that you might talk about. But it's a nice combination of the seismic recordings on the left-hand side of the screen with stations shown on the surface and the actual waveforms propagating through the Earth and arriving at each station. So at this point, I'd like to take another brief pause to allow people to jot down some notes, maybe ask a question or two, if anybody has questions at this point. Or if not, just a few ideas for processing, maybe some ideas that you now have.
Hey, Michael, Aida again. One of the conversations I'm having here with a couple of people is about the data that you use to get to the 108 degrees. So it's one event with data points from many different locations that felt that event.
That's right. So let me go back to that slide. So we're looking at one event, and each one of these triangles is a different station around the world recording that exact same event. And so you can see that there is a delay as the waves travel around the Earth, through the Earth, to reaching each one of those stations.
And so just thinking that it would be interesting to maybe have different classes look at different events and then compare across classes, but lots of different permutations you could come up with to build out a bigger data set there to compare.
That's right. That's right.
Yeah.
So kind of, what we had done here towards the end, where we were rotating this model around on top, we were having earthquakes take place at different locations. You could start off by having different seismologist groups of 3 work pretty well for that activity. So different groups of 3 being seismologists could have a different event to use to start with, which would then be similar to what you're having them do here at the end, where they're actually turning that piece of the model. Okay, for the sake of time, let's kind of move on. So if you really want to get modern with your seismology instruction, you could extrapolate this out to another one of the high school standards, where we're talking about collecting and using scientific reasoning and evidence from ancient Earth materials, meteorites, other planets, to account for Earth's formation in early history. Right? So how do terrestrial planets form? Well, we know that the planet starts through the process of accretion and bringing material together. We also know then that it heats up, the interior begins to melt. Step 3 is stuff happens. It's really not that well understood, certainly for planets, other terrestrial planets in the solar system. But at the end of the day, we end up with a crust, a mantle, and a core. And so one of the ways that we're currently studying this is with the InSight mission. So NASA landed a lander on Mars that you've probably heard about, the InSight mission, where they deployed a seismometer. And that data is now coming back and being streamed into the IRIS Data Management Center, and you can get access to this data in your classroom. Now, right now, there isn't enough data to be able to actually determine the interior structure of Mars, but that is an active science project that they're working on. In fact, at the last AGU meeting just a few months ago in December, the first results were being shared about identifying number of meteorite impacts, the number of Marsquakes that they're experiencing on Mars' surface. And so that data is available for you to see 24 hours a day with a delay. There's a time delay in that when that data comes back from Mars. But you could see it in near real time as it comes in your own classroom. And we'll talk a little bit more about that in a few minutes. So that would be a really modern update to your classroom. So the second option that I thought about was, well, there's going to be some people who do not want to abandon the earthquake location. And so for those people, I would say, that's fine. It probably would fit into the middle school level then, where we're talking a lot about using the location of earthquakes to define plate boundaries. So an obvious question for students might be, well, how do they know where these earthquakes happen if they happen in remote Alaska or somewhere in the South Pacific where people don't really live? So we could talk a little bit about seismometers and how they work. And then we could talk about how we actually locate earthquakes. So here is an alternative to the S-P location. So on the left, I have a map. You can see that, I hate to do it, but I'll drag out the drawing tools again. This is Japan right here. Every one of these red triangles is a seismic station. And so on the right side, we now have, again, one of those record sections, only it's plotted in the reverse axes. So time is now going on the x-axis with time since the event, a 0 time or when the event took place on the left, and then time since the event going out to the right. And then the number of degrees away each station is from the event is on the y-axis on this plot. So clearly, when I look at my seismic recordings, I can say an event happened somewhere, but where? I don't know where. So how might you begin this? Take a moment and think about how you might start to tackle this problem. So one of the ways that you might tackle this problem is by using an approach called the bisector method. So the bisector method says, okay, we're going to actually start by comparing two stations, and we're going to use a process of elimination to find out where this earthquake probably happened in the world. So I'm going to compare these two stations here, and I'm going to connect these two stations with a path. And in the middle of the path, halfway in between the two stations, I'm going to draw a line we're going to call a bisector. And the idea here is that we want to compare which one of these stations had the seismic waves arrive to it first. And if we know which station it arrived to first, we can tell which side of this bisector line the earthquake had to have been on. So we're going to compare Tato and Wake, and we're going to decide which half of the map the earthquake has to be on. So use the chat box. Which station was closest to the epicenter, Tato or Wake? Yep, I'm seeing some votes for Tato start to come in, and you're right. So Tato, the seismic energy arrived there first, and so we know that Tato has to be closer to the earthquake than Wake is. And so if we go back to our map, that means that everything on the Wake side of the line can be shaded out. And if we shade that area out, we know the earthquake can't be anywhere in that section. And so we then go through a process of elimination, and we create pairs between all the other stations that are on the page. And what you end up with is a solution that looks like this. So this was I had shaded out this entire activity. And you end up with a small triangle near one of the stations where the earthquake had to have been. And you might have been able to come up with, I can't guarantee I did all the pairs there when working on this, but I did most of the pairs, and I got it down to this very small area. So you do have to have pretty good station coverage, a fair number of stations around the event to use this location. But if you do use this, P waves are much easier to pick than S waves are. In fact, a lot of times S waves don't show up very well if you're only looking at one seismogram as opposed to, like I said before, 3 seismograms. This process of using P waves only is much closer to how we actually locate earthquakes, and so we're modeling that basic idea. Right now, we don't have an automated way to do this, but within the next few months, we're working on developing this tool. So we will have an online bisector location activity for students to be able to do on the screen. And so it gives a new way for us to locate earthquakes. Again, this still isn't quite how we do it, but it's closer than the S minus P method. So I'll take a couple of questions since I introduced a new idea for some of you.
Okay, Aida again. One of the thoughts was that in thinking about that more traditional earth structure activity, there are also, as you noted, some other uses for seismic data, like looking at riverbed load. So are there activities for any of those kind of non-traditional classroom type activities available online on IRIS's site?
There are. So there are for some. I will show you a couple at the very end of the talk as well. So I will show you a couple, and some of them are really new and we don't have anything. Bedload is one we don't have anything yet, but it would one that we would love to.
Great, thanks.
Somebody's asking if we can provide a source for how the epicenter is really determined. So let's go on. So a better approach, there would be a better approach, and this is the way that we'll talk about how we actually are going to locate earthquakes. So if I gave you this same setup, now having seen the bisector, what might you assume right away? So if I gave you this data and this set of stations, what would be a back of the envelope calculation for where the earthquake is? Right. So the most obvious place to start, somebody just posted into the chat box, is, well, it's got to be close to this station, right? This station is pretty close to the epicenter, not a lot of time between when the event happened and when the seismic waves arrived. And we did find that when we used the bisector method. So you might just start about that point. So the way we're going to actually solve this inverse problem is we're going to say, let's make an initial estimate of where that earthquake is. And we're going to assume that it's the closest station to the epicenter. We're then going to use a velocity model to predict P-wave arrivals for that location. So think about the velocity model that we used in our Earth structure activity. We assumed 11 kilometers per second. Same basic idea. We're going to use a computer and we're going to predict when the seismic energy should arrive at all of those stations if the source of that energy was that closest station. And when we compare the predicted values to the actual values, we're going to get an error. And if that error is acceptable, we're going to tell the computer to stop running. And that's the location. However, if the error is unacceptable, we're going to tell the computer to adjust its location using some parameters and then repeat it. So move it in a direction that's likely to give you a lower error and repeat the process. And it will continue to run this loop of trying a solution, predicting the values, comparing the predicted values to the observed values, and seeing how close the error is. And it'll continue to run this loop until we reach some sort of acceptable level of error. And that's how we actually locate earthquakes, using only P waves. So this is the modern process, the really modern process that you might want to consider using with your students. So to be able to actualize this, we are developing a tool called EQ Locate, and it's in beta mode right now. So it works, it's available online, but we haven't publicly released it yet because we're still kind of tweaking it. But I'll give you a quick walkthrough of it. So we get a set of stations, and we get seismograms for those stations that you might use. And I'm going to share my web browser. So I've gone in and I've picked out some stations that I want to pick seismograms at. And I'm going to say, where did the energy first arrive? Because the time of arrival of the actual waves is really important. So I'm going to go through all of these and I'm going to pick locations or pick times on the seismogram when I think the seismic energy got there. And I'm going really fast for the sake of this webinar. And then once I've done that, I'm going to go up here to next. And so what I get is I get error bars shown, and it's called, this RMS error is shown here. And as I move my location around, so instead of having the computer picking new locations over and over and over again, I'm actually going to begin to move that around. And as I do, you see that the error changes. So if I go really far away, I get some really big arrows that are showing me really large amounts of error. And we can see error in the lower right-hand corner as well. However, if I begin to get into the ballpark of where the event is, you can see I get to a green level of error where I have an acceptable value, and we would call that the location of the actual event. So that's how we actually are locating earthquakes. And just for the sake of time, we ask for a couple of examples. In my slide deck are how you can get to Mars data, but I did, because the question came up, here's an example of where we could work towards using non-traditional performance expectations. So we could ask what's shaking in Greenland here, where we have the number of icequakes that are happening in any given year in Greenland, and we can see a pattern happening. And so you might ask your students, why do they think this is happening? What do they already know about glaciers? Because here's the locations of these events. You'll notice they're all on the edges of the glacier. Your students might guess that it has something to do with temperature. So if I rebin that data, I can bin that data so that it's by month, but all the years combined, and we see a pattern. Sure enough, in the warmest months, the number of events increase. So then we can take that data and we could address these high school standards by looking at issues of climate change by comparing air temperature to the number of icequakes that are taking place. And so we could talk about flows of energy into and the interactions between various systems that we're measuring. So ground motion caused by these icequakes, and they're a source of these being connected or correlating well with changes in air temperature would be one example of a non-traditional source. Another one might be looking at induced seismicity. So we might look at our earthquakes and we might address a content standard around the idea of natural resources and our demand for natural resources and how that influences our Earth spheres based on our extraction of natural resources. So again, another activity that students might want to use in the classroom. And with that, I'm going to stop at this point. We're about out of time, and I know there's a couple of slides that we want to show at the end for upcoming webinars and whatnot. But if people have questions, I'd be happy to answer them now, or I'd also, of course, be able to answer them later as well. My email's on the screen. So please send me an email, or I look forward to meeting you at some point at NGSS, at the NSTA meeting or other meetings.
We do have a couple other questions.
Sure.
So first of all, one of the teachers was interested in piloting earthquake locate and wonders if there's opportunity to do that. So perhaps you want to connect with them offline. I don't know.
That would be great. Yes.
Okay.
Yes.
And then an observation that when you were using that tool, there was a depth slider at the top, it looked like.
Yes.
So
yes.
That's another way to be more precise in your location, is to use that depth slider. And does it give you depth measurements then?
It does. So you can change the depth estimate. So I was only focused on the sort of latitude and longitude adjustments just in that quick demo. But if you were to refine it even further, you could change the depth of that event, because it really is a three-dimensional solution that you're after. And you can further increase your accuracy by adjusting that depth, by assuming certain depths. So again, the computer would be normally taking into account depth factors as well.
Okay, then there was one other question that I saw in the chat. Is there an easy way to get a 3-component seismogram from IRIS?
It's a great question, and unfortunately right now there is not one. The tool that we had isn't working right now, and so we don't have a really great way for the average citizen to get that data. But that is something that we're working on repairing, and so we'd hope in the next 6 months, if not sooner, to get that up and running again, so that people can actually work on it. There are ways that you can get it easily if you're willing to go through some pretty tedious menus. But if you want something for a lab activity, I'd be willing to help get that data for somebody who would really like it. So you can send me an email, and I can, in the meantime, I can help plug the leak.
Thanks. All right, do you want to run through the next couple of slides there?
Sure.
We'd love to get to the one that has the link for the survey, but the post-webinar survey link is in the chat box, and we would really love for you to fill out that post-webinar survey, especially if you would like to have a certificate of webinar attendance, which you can now get after you fill out the survey. So once you fill out that survey, you'll find a link there to another form where you can enter in your name and email address, and you will be able to then receive our post-webinar attendance certificate. So we'd love for you to have that as well. Go ahead and move forward. And again, the link is in the chat box to get to that. This webinar series is brought to you by 3 organizations, and that is NAGT. You see the slide there. NAGT has a webinar about every week. So drop into the NAGT website and look for those webinars. Next one. Also, the National Earth Science Teachers Association, NESTA. And you can see a link there to NESTA. The third organization, which I don't think we have a slide for right now, is the American Geosciences Institute. Look for some exciting announcements from AGI. And again, upcoming webinars, registration is open for the March webinar mini-series, which will focus on questioning in the classroom. 2 great webinars there. We hope to see you all on those webinars. And go ahead and forward through to the last slide, I think. Or one more, I think. We'll go to one more. If you'd like to reach out to any of us, to Ed Bobeck, Carla McAuliffe, or myself, I think you'll find our contact information on the next slide, perhaps. If not, that's okay.
That was it.
That's okay. We're fine there.
Okay.
If you want to go back and view any of our archived webinars, you can view them at bit.ly/webinar NGSS. At this point, I'd like to say thank you very much to Michael for joining us. What a great bunch of resources and lots of new things for us to think about in terms of modernizing the way that we're teaching our students around all the resources that IRIS offers to us. So thank you very much, Michael, for presenting for us today. And we look forward to seeing everybody on another webinar in the future. Thanks for joining us. Have a great afternoon.
Great, thank you.
Thank you, Michael.
Thank you, Michael.
Of course, sure, my pleasure.
It was fantastic, as always.